Welcome to your 3-month hands-on certification program in pharmacometrics and PK/PD modeling using RsNLME. So today is our last day of the workshop. Thank you all for being here with us and going through the journey with us. In the past 3 months, we really enjoyed working with you, walking you through the various aspects of pharmacometrics and PK/PD modeling. We had our module 1, which was covered by Sir Go-Z, which was on the fundamentals of pharmacometrics and PK/PD modeling. And then for module 2, we had our own Dr. Rajan cover the fundamentals of using R. And our module 3 was covered by Keith. And Keith is an expert modeler as well as the primary author of RsNLME. And you are actually learning from the best. So without further ado, I will pass this over to Keith to continue on our journey with RsNLME. And I would strongly encourage you to ask questions. And also wanted to share with you that we will be giving you a month's time, so you are able to work on the various other aspects. If you missed any sessions, or if there are homework assignments that you want to catch up on, so you will have the time. Again, please reach out to us if you have any questions or having any issues with your RsNLME, and we are here to support you. So without further ado, I would hand this over to Keith.
Great, thanks, Aruna. So welcome everybody. And again, it's hard to believe this is already the last session, but I think we have a pretty good agenda today, and we'll be able to get into some of the additional steps and additional functionality of how RsNLME can support the pharmacometric workflow. So I go ahead and get started. I think by now everyone's familiar with Muli. Thank you, Muli, again for your tireless efforts in getting everyone set up. Just as a side note, I'd like to thank the audience, as not only has this opportunity been good for us to share what we're working on and what's coming in the future, but also with any new tool, there's rough edges that need to be smoothed out, and your feedback is critical for that. And again, please do not stop continuing to give us the type of feedback that lets us improve our software. So this is the original agenda. What I'd like to start with is essentially just a recap. So last session, what we did is we created a Piranha project and explored our data set using Piranha's data inspector. And then we took a look at the open source R package ggquick-EDA. It's a great way to both use ggplot2, but also learn that code. Again, an underlying theme and why we built these tools the way we built them and based them on R. We learned how Piranha is able to create R code that you can either run directly from Piranha or copy that into an R session and modify it to suit the exact needs of the display that you want to create. We then created a PK model from within Piranha. We launched the Model Builder Shiny application, created a model and fit that model using an additive error model, which is the wrong error model. We'll take a look at that when we move forward. We looked at the run summary output in Piranha, kind of looked at an overview of how Piranha supports like run organization and how it organizes your files for you, and then explored some of those library diagnostic plots. And then we learned how any of those plots in Piranha can be, again, the same theme, opened in R for further customization. So what I'd like to do today is refine our base model, And we're going to run a multiplicative error model, but also take a look at, some of the diagnostics that would suggest that your error model is wrong, and maybe dive in just a bit into the math behind some of these error models, as well as some of the covariate models. Now, when I do this, I think, I'm not proposing that this is the way that it must be done, right? I'm sharing how I think about interpretation of these models that we use, because in the end, they're algebraic equations, and they are sometimes enforcing relationships in the fit that you're trying to make. So it's important to understand what relationships those models are, specifying, because the math can be tricky sometimes. It's not hard, it's just counterintuitive sometimes in terms of how it works. So I have some slides, and I also have some very simple scripts in R to show you how you can use just base R to further your understanding about what you're actually doing in your modeling process. So we'll refine that base model, then we'll take a look at adding covariates to the model. We'll do a graphical exploration of potential covariate influences with our base model. We'll then add a covariate model to our model manually and take a look at what you should see in diagnostics if you have an important covariate effect. And then we'll execute an automated stepwise covariate search. So this is a tool that actually a lot of modeling tools have this, but it automates the kind of tedious process of running many covariate models and post-processing them. And we'll show you how to do that with RsNLME. Then we will take a look at how to create a special diagnostic called a visual predictive diagnostic. And we'll do that on what we call our final model. And then finally, we will run a basic simulation with our new model by creating a data set with a new dosing regimen. And that should give you a good feel for like a complete workflow and how this is implemented within RsNLME. So with that, I think I'll jump over to Piranha, and we'll open our model from last week. And again, if you have any questions or would like to stop me, I'm extremely flexible as to how we spend this time. So please, raise your hand, speak up if you have questions, and we'll just keep going. So recall that in this model, we had specified an additive error model. Okay, and we fit that data, and the fit looked okay, right? We take a look at some of our residual plots, however. When I open the res versus ID, for example, I'm sorry, independent variable, if it opens, double click. Here we go. Right, so often if you've read papers or talked about modeling, right, a lot of diagnostic plots, the goal for these is to see kind of even distribution around some reference line, with the plot being rather featureless with respect to patterns. And this is a classical funnel plot, they call it, that suggests that you're using an additive error model, and perhaps multiplicative would be more appropriate, right? So how do you think about this stuff, right? And when I was learning modeling and learning R, I would always go back to examples in R. And if you think about what you're doing when you're specifying an error model and what you're actually estimating, what you're estimating is a standard deviation on a distribution, right? And that distribution that you're estimating, you're basically assuming that distribution fits the nature of the data that you're trying to fit. And to graphically visualize this, what I've done is I've just done some very simple scripts in base R. And again, don't get too caught up in the code. This par mf row, this is just a way in base R to split your display into 2 rows by 3 columns. very, very handy. But in this code here, I'll just step through this, but I've done this for an additive error model, for a multiplicative error model, and then for a combined error model to help the group visualize what these error models are really doing and what you're actually fitting. So what I've done is I've created a CPRED variable and said, okay, CPRED, it's just a string of numbers from 1 to 1,000, right? If I run this, we can look at CPRED. Sorry, I clicked on the wrong one. Well, here, I'll just highlight it and run it, right? 1 to 1,000, just a vector of numbers of 1 to 1,000. Then what I've done is I've created a distribution, and this distribution is a normal distribution with 1,000 points, mean of 0, and standard deviation of 40, right? And the error model that we use when we use an additive error model is saying, okay, our C observation is going to be our prediction plus some error term that is drawn from this distribution. And when you graph this, right, this is what it looks like. And in the graphs are where, let me just change the part here. The graphs are where you really start to understand what's going on here. So with this error model, what you're doing is, as Sergey pointed out in his lectures, right, you're making the assumption that the error around your predicted line is of the same size, the same absolute size, regardless of what concentration you're at. So this might make sense for like PD variables, but usually for, you know, PK variables, if you look at an assay, even for example, how is an assay reported, right? They give a CV. You know, the performance of the assay was 5% over a concentration range of 0 to 1,000, right? So they don't say the absolute error of the assay was 5 over a range of 0 to 1,000. So right there is a hint that, you know, maybe the nature of the data is not suited, because again, you're trying to estimate, what are you estimating, right? A standard deviation, right? And when you assume this type of error model, that standard deviation is basically this spread here, right? And if you look at this in terms of, you know, a concentration time profile, right? So what I've done here is I've basically said, okay, time is a sequence of vector from 0 to 24 by 0.1. So that's 0 to 24 hours by 0.1 is my time scale. And then I just have an equation for a 1-compartment model, right? A dose times Ka over volume times Ka minus Ke times Exp. Just a very simple PK equation. Hopefully you're getting a sense for how you can use R to understand, you know, what's going on a bit better. And then I create a, again, a normal distribution. This time I use the number of data points in my little example here. I apply my error model, then I plot. So I'll just run everything so the 3 plots come out next to each other. And what we'll see is this. Now, when you look at this data, right, again, additive error model, this is this picture reflects the assumption you're making in terms of what your data look like. And if you look at these profiles on a log scale, what is this saying? It's saying that the size of the potential error in the assay or in the observation, right, at lower concentrations, the absolute size is the same as it is at higher concentrations, right? So this kind of funnel-shaped look in a log profile, right? If your data actually looked like that, then okay, perhaps an additive error model would suffice. However, if we look at our data, and this data I generated just by going to my Piranha and copying out of the data inspector, but I'll just run this quick, right? If we look at our actual data set, you know, I've limited it from 0 to 24 hours. You know, does it look like this funnel shape? Probably not, right? It kind of looks like it's relatively stable through the, you know, the variability is concentration, proportional to the concentration, kind of hinting at a multiplicative error model, right? So again, if we do the same exercise for a multiplicative error model, I can share this code if people are interested. Let me just run this. Here we go. Okay, so here we have an additive error model on the top, and then a multiplicative error model on the bottom. And you see the difference. So here, the error in the concentration is proportional to the value of the concentration. So at high concentrations, it's higher, and at very low concentrations, it's lower. Your plot on a log scale would look more like this, right? Which if you have analyzed any types of PK data, right, normally the error that you see is larger around the peaks than it is, you know, down at the lower regions of the assay. And on a log scale, it's more evenly distributed, right? So if you compare it to, you know, our plot that we generated before, right, it kind of looks more like that, right? The problem with, not problem, but one of the limitations of a pure multiplicative error model is that at very low concentrations, right, it says the size of your error actually begins to approach zero, right? When in reality, we know that assays error doesn't go down to zero when the concentration is very small, right? There's a, you know, usually a limit of quantification, or there's a set point where, you know, the assay is just not that good for measuring below that. And that's where the combined additive error, additive and multiplicative error models come in. And if I plot the same, again, the same plot, and I'm pulling these equations like for these error models directly from the PML code, right? If I run that, what we'll see, right, is it's kind of in between, right? Additive in a multiplicative error model. So this additive plus multiplicative will have the characteristics of a multiplicative error model in that, you know, your error is proportional to concentration, but it reaches a limit at the lower concentration and says, okay, you know, the error can't go any smaller than this because you have that additive, you know, error component that's added in. So I hope that's helpful. Again, it's the way I think about this. I'm not saying it's the way that it should be thought about it. You know, you sometimes watch YouTube channels and they say, I'm not saying this is the way you do it. I'm saying this is the way I do it. So hopefully that was helpful. Now, if we go back to Piranha, right? So we saw the residual plot, right? If we look at residual versus predicted, let me just double click on that. Sorry, my Piranha is a bit slow. I was hoping these would come up faster. Come on. All right, so this is a residual versus pred, right? And what do you see in this plot? Again, as pred is increasing, right, the shape of this curve is kind of funneling out, right? So what is it saying? It's saying, all right, I applied an error model to this that says the error, or the size of the miss across my concentration range is the same from very low to very high concentrations. And these funnel shaped plots, right, basically say, well, you know, Keith, your data are showing that the size of the miss at your higher concentration levels is larger. So I hope you can see how this type of plot of, you know, residuals translates back into what's going on here. I'm trying to fit this model when in reality, my data look like this, right? So my errors are going to be larger at higher concentrations than at lower. So again, I'm trying to give you a feel for how to think through interpretation of some of these error models. What we're going to do now is modify this code and just use a multiplicative error model. So we can duplicate this model and, you know, give it a new name, duplicate. And instead of COBS equals C plus, I'm going to do the multiplicative error model, which is times, in parentheses, 1 plus CEPS. And I will take and run this, and then what we'll do is we'll compare those diagnostics. So I'll just fit MetaModel quickly. This will run. I think I'll try to do these models live if it gets to the point where it's delaying. I do have a separate project where I can just jump to you know, the examples that I want to show. So we'll let this one go. Should be pretty quick. It's generating the outputs. Okay. So now I have my new model. Now notice the objective function decrease. You can't really look at the objective function because this is not a model with 1 degree of freedom difference. Rather, you've changed like structural components of the model. So sometimes a better kind of diagnostic variable to look at is the IKK criteria. Piranha allows you to quickly compute this. Now, as the text says, there's subtleties to the appropriate calculation of IKK. I'm not the guy to get into what those subtleties are, but there are functionalities where you can weight various elements of the calculation. But for a gross view, if we just calculate IKK for both of these, you'll see that there was a drop, right? 1900 down to 2500. So that's, suggesting that this model actually is a better fit. And if we go and we then compare, now one of the things in Piranha, you can highlight more than one model and run diagnostics, and you'll see, the diagnostics side by side. So let's look at residual versus the independent variable, which is time this time. So we'll run that script with 2 models highlighted. What's going on here? I'm not sure why that's not working. My apologies. Just bear with me for 1 second here. Not me. Well, here, maybe we'll go up, make the point up here. Make sure this runs. There we go. Sorry, I think I may have had something open. So let me try this again. Cool. Come on. Finally. Okay. Apologies for that. I think I had my Adobe open with a previous view of that, which was what was causing that error. But again, we go back and we look at the additive error model, our run 1, and you see this funnel shaped representation. We look at our proportional or multiplicative error model, and this is the type of featureless display with even distribution around the line of reference that you like to see. So drop in IKK plus an improvement in diagnostics suggests that the multiplicative error model is a appropriate error model. So, okay, that's all I wanted to say on residuals. So I'll bring back my PowerPoint slides here, and next we're going to develop the covariate model. So really the purpose here is you're looking to identify and quantify the effects of variables that influence PK or PD of the drug. Why? Well, you'd like to understand that prospectively in case, for example, you have a patient population that behaves differently with the drug, and you might want to dose them differently. Would be a very simple example. Probably the simplest example of why you want to do covariate analysis. And the general process is you define the set of covariates first, right? That you're going to evaluate, and you need to plan this and include them in your data set. Usually, this is done well in advance of the analysis. Any population report done today now has an analysis plan that talks about the characteristics of the drug, what covariates you're going to collect, why you're going to collect them. And then the critical thing really is you need to design the study, the case report form, the data collection methodology to collect that information with sufficient detail to put it into a nonlinear mixed effects model data set. And again, these data sets are special because it's an event by event recreation of dosing and observation events. If you're working with covariates that change over time, then that essentially is, you can think of that like an observation, right? What do you need? You need the covariate value in an accurate time. And sometimes covariate might be taken at baseline and then that's it. They take it at follow-up. Well, you might want to design your study to collect that more frequently so you can get it into your data set in a way that's useful for the way you plan to evaluate it. What are the covariates, right? It's the usual suspects, demography, right? Plus any drug-specific, disease-specific, factors of interest. And that really is where, in drug development, the answer is, well, it depends, right? So you have your covariates, you plan well, you have a good data set. The next step is to graphically explore them. And here is where, you're basically creating plots of individual parameter estimates of clearance volume, right, versus the covariates to see if there's relationships. You also look at ETAs versus covariates. So again, what's an ETA, right? When you run a base population model, you determine a clearance value. Let's think about clearance. And that clearance value is basically one value for the whole population, right? And then what is the model also doing? Well, for every individual in that population, it is pulling a error term, right? 1 for one patient, 2 for another, 5 for another, -2 for another, right? And that ETA term, the direction and size of it, right, is dependent on that person's individual data. So if you have a relationship where heavy people clear the drug faster, right? And your model is predicting the same value for heavy people and light people, right? Your ETA terms are going to be positive for heavy people and maybe negative for very light people, right? So when you plot weight versus ETA, you're actually seeing, okay, the direction and size of the area by that covariate, and you'll see patterns very easily. And we'll take a look at that. And those patterns, again, just like with the residual error model, when you add covariates to your model, you see them disappear. It's actually quite rewarding to kind of work through these types of models and see as you add covariates, you're explaining variability, you're seeing improvements. Kind of fun to do. And it's, pharmacometricians say it's part statistics, part art. And that's where the, maybe a little bit of the artistic comes in. So after you have an idea of what covariates you want to look at from your graphical exploration, you start to do model runs. There's single covariate runs where you add a covariate one at a time, evaluate the model improvement in terms of the objective function, change in parameter estimates. As you add covariates that explain variability, you expect your omegas or your between subject variability terms to go down. So these are the types of the things that you're looking at, continuing to look at the diagnostics for improvements. There's many ways to determine final covariate models. I think in reality, 10 years from now, it's probably all going to be machine learning and automatic. I'm not the guy to kind of contrast the various methods of covariate model development, but a very classical way is what they call forward addition, backward deletion. And forward addition is where essentially you run all your covariates models one at a time, and you pick the one that had the biggest influence. And then you keep that one in the model and you repeat. You add all the other covariates one at a time. Pick the one that had the most influential, and now you have 2, and then you repeat that. And when you get to the point where adding additional covariates doesn't result in any, improvement in the fit of your model, you say, okay, this is my full model. And then you try to drop them one at a time to see if there's model worsening. And if there's no model worsening, you can eliminate that covariate from the model. And the reason that you're able to drop is because there's correlation between covariates, creatinine clearance and weight, right? If you use the Cockcroft-Gault equation to calculate creatinine clearance, then, well, it's going to be correlated to weight. So it could be that you add weight to the model and the creatinine clearance relationship falls out. That's what's going on there. And then your final model is essentially, okay, the model that you end up with after this process. And you can do further diagnostics, tweak it more. Again, it's a very iterative process. You might do this, several times to come up with a model that does what you need it to do. So again, we're still in conduct analysis. What we're going to do is explore some covariate model diagnostics. We're going to execute a single covariate model run. We're going to then look at how you can do a automated covariate search in using RsNLME, and then we're going to combine our findings into a final covariate model. So, again, like we did with residuals, I just wanted to, make a note on covariate model equations, right? And when I was learning this, population back in, well, I don't want to admit how long ago it was, but, this quote from Henderson and Vellman, right? The data analyst knows more than computer, right? If you don't use that knowledge, you're going to produce inadequate data analysis. So it's very tempting when using data, modeling tools, right, to hit the go button and then just look at your results, right? And what I want to point to is that, take the time to understand the math within your covariate models, right? And by that, I mean, is the relationship that you're specifying with that model consistent with the data? Just like with the residual error terms, some of these covariate models specify a linear relationship. Some of them are able to fit a curve, right? With this covariate model, what do my estimated parameters actually mean? Centering, when we center on a value, what does it mean to my parameter estimates, right? What is this concept of a reference subject? What's a typical subject, right? With the models that you're applying to determine covariate relationships, you should be very clear, right? What these models are actually doing. Now, what I'm going to do is just go through the default models for continuous and categorical covariates in NLME. And these default models in NLME essentially represent covariate influences as shifts in the parameter of interest, so clearance or volume or what have you, from the value estimated for a defined reference subject, okay? Now let's take a look at that. What is that actually saying? So if you look at the default model for a continuous covariate, right, we have clearance equals a typical value of clearance times, we'll look at weight, for example, and we have weight over 70, so it's normalized to 70 raised to the exponential dCLD weight. The dCLD, dVd, that's just NLME convention, but this is what you're estimating here when you're adding the covariate effect. So for this model, TVCL, really what it is, it's the value of clearance in a 70 kilogram subject, because 70 over 7 is 1, and 1 raised to any power is 1, right? So if your weight is 70, this part drops out, you're left with TVCL, which is clearance in a patient of weight of 70. Now, what would clearance TVCL represent if weight were not normalized, right? Assuming that dCLD was not 0, which would make this 1. So it would drop to CL equals TVCL times weight raised to the dCDL weight, right? So what would TVCL be if weight is not normalized? Well, if weight was 0, right, it would drop to 0. If weight's 1, right, the way to think of it, what would make this 1 if weight were 1, right? So TVCL in that case would be the clearance for a subject of weight 1, which doesn't really make sense if you think about it. Who in your data set or who that you're going to be simulating, unless you're going into the pediatrics, right, is going to have a weight of 1. So think about how your models are structured. The other cool thing, and one of the reasons it's selected by a default as a default model, is because when dCLD weight is allowed to range from, for example, -2 to 2, this model structure can, define a linear relationship, no relationship, or a curve. And it's easy to see that. If we jump into R, right, again, what I've done is I have a very simple code, right? I have a weight variable, that's a vector 45 to 120. I'm setting my dCLD weight, or that exponential term, to just a range of values, -2, 1, right? And I'm just fixing my TVCL to 10 for these examples, right? And when I do that, I then have a simple for loop. And again, I can share all this code. Don't get too caught up, but you can write for loops in R. So I'm saying, okay, for I in 1 to 7, because there's 7 variables here, right? I'm going to calculate clearance, where clearance is equal to TVCL. Now this should look like the equation that we're fitting in NLME, right? Clearance equals TVCL times weight over 7 raised to the DCLDI. So that's basically just picking out the ith, vectors of the ith position. So in the first iteration, it'll pick the first position, it'll be -2. When it loops through again, it'll be -1. And if we run this, right, what we see is this. Now, again, what are we looking at here? So when you fit using this type of model, right, depending on the value that's estimated for your DCLD weight, you can specify any one of these relationships here. So it's very flexible. Now compare that to a linear model where you could only, estimate a straight line. Again, this is where you're looking at your data, you're seeing the patterns, and then you're deciding, all right, is this an appropriate model? Can I fit that pattern with this kind of model, right? Likewise for categorical variables, I think I have a slide, but for categorical variables, basically what you're doing is the way the default models in NLME are organized, you're treating these as a shift from a reference subject. Usually it's, whatever demography is more common in your data set. In this example, I've said, okay, males are more common. So females are then, a shift from the male reference. And, again, with the DL, we'll go over this math, but the standard uses an exponential. And my point here is just to show you how the exponential term that you're estimating translates into a, -2 translate into essentially a 14% of male reference, whereas 0.5 translates into females being 1.65 fold higher. So maybe I jumped ahead a bit there, but all right. So let's go back to covariate models. Yeah. So again, we saw this. So my point is know what these models are. Look into the math, understand it. It's not that hard, but the more you work with it, you'll be able to look at equations and see the pattern behind that. Here, the default model for categorical covariate, I just want to explain this because it is an example of one that's a little less intuitive. So it's TVCL times, and then PML will say, okay, we're going to do this by having exponentiating DCLD sex, right, times sex equals 1. So what's actually happening in the background with this model, right? Sex equals 1 is a logical check, okay? And if the condition is met, it will return a 1. So in your data set, you have sex equals 1 for female and sex equals 0 for males, right? And clearance would be, TVCL would be the value of clearance in a reference male subject, Y. All right, so if sex equals 0, this logic check will return a 0. So then it becomes DCLD sex times 0, EXP 0 is 1, drops out of the equation. If sex equals 1, then this returns a 1. And you'll basically have CL equals TLCV times EXP to this term. And we looked in the previous graph, I think I have a slide next, right? What that term is actually translating to. It's a scale factor for the condition where sex is female. This is, I already explained this. Yeah, so, okay. So now let's take a look in Piranha for how to do this. And okay, we have our multiplicative error model. Now, when we created this model, right, we added some covariate influences. And what we want to do now is use this model to run some diagnostics. So the covariates are in there, but we haven't applied them to any of the parameters, right? So here we have in our parameter estimates, right? We have volume, clearance, V2, CL. What are these actual numbers, right? This is one number that's kind of in the middle of the population data set that we fit. Now recall that each one of these subjects has a individual error term that let's look at parameters first, that is created for them based on their data, right? So if we look at parameter versus covariates, and again, here we're just trying to understand what the general relationships are in our data. It's a bit slow. I'm surprised how Zoom can slow down programs, but okay. So let's just kind of skip through these. So here we have volume as a function of weight, right? Now, this is not TVV, right? This is V. So what is V? It's your typical volume plus your eta term. So this is individual estimates of volume based on patient data. And here you can very easily see that volume appears to be larger for heavier people, right? So we just flip through these. Clearance. Again, there appears to be a weight relationship on clearance. Volume 2, now remember, we don't have an eta term on V2 or CL2, right? So this is just presenting, all right, the V2 is in between, well, 99.31, right? So those aren't too useful. If we wanted to, we could go back and add eta terms to these two model parameters, and then we'd see similar plots. Again, for the purpose of this course, I just used etas on clearance and volume. Creatinine clearance, not surprising. We see something there if we see something with weight, right? Both on volume and clearance. V2, we'll just skip by these. Age. Now age, I don't know, maybe something, right? But you don't see as clear a pattern as you do with weight, right? Same thing for clearance, possibly, possibly something there. The more you work with these types of models and the more that you stare at these types of plots, the more you'll be able to interpret them. Again, it's just a numbers game in that respect. Gender, right? It's categorical. So it's by default presented as box and whisker plots. And here it looks like the volume is lower for females versus males. Now, could that be weight? Maybe. Same for clearance, right? V2, again, we'll skip by. Center effect, I don't see anything there, right? Doesn't look like center has anything to do with our parameters, right? So at that point, I might just say, all right, I'm not going to worry about center in my covariate analysis, right? Another interesting plot to look at is to just look at your covariates in your data set in a scatter plot matrix. So I'm just going to run that quick and we'll take a look at that. And why do you want to do this? It's so you can see whether or not any of your covariates have, correlations that you might want to not worry about, but just understand, right? So this is very, very useful plot. So here you can see that weight and creatinine clearance are in fact highly correlated, right? 0.906. So I would suspect, right, that it's unlikely that both of those covariates might end up in the model, unless, maybe you have a drug that's highly renally cleared. Sorry about that. I think age, right? There's definitely some correlations here, right? Gender versus weight. You see males higher than females. So it's useful to look, at this this type of plot to understand your data set, right, in general. The other thing you can gain from this is okay, say I'm going to add creatinine clearance to my model, right? What's the range I'm actually looking at here? Well, my data set has a creatinine clearance range of 70 to 120 maybe, right? Am I going to be able to say anything about, how this drug behaves in renal impairment? No, of course not. Your data set does not have the data needed to make that kind of statement. And that's another important kind of back consideration that you need to be thinking about when you do these types of analyses is the population data set that you have, right? Is it sufficient to draw the conclusions that you're trying to draw, right? And that's where it all gets back into, all right, how are we designing this trial? The inclusion exclusion criteria. Are we getting the patients that we need to defend this, maybe signal that we have an issue in renal impairment, right? So it's all, yeah, everything's related. But yeah, this is a very useful kind of plot. So what we're going to do is we're going to take this model, make a copy of it, and we're going to do weight on clearance. We'll call it weight on clearance. So we're going to add a weight covariate. And the way to do that, right? Of course, we saw the equations. You can always go to the model builder and kind of run a model and say, okay, add a covariate and then copy it over. I'm just going to edit this text directly. And it's fairly simple, right? We have the equation from the PowerPoint. But you simply go in the clearance area. So we are going to do times weight over 70, right? So we're going to normalize. I should probably use capital weight, right? And then we have raised to the DCLD weight times EXP A to CL. So now my clearance equation has a factor for weight in it. And what's the other thing we need to do? We need to define the fixed effects, because that tells NLME, hey, okay, now I have this DCLD weight covariate that or parameter that I want to estimate. So it's simply just like for the other parameters, fixed effects, right? DCLD weight equals, and then here again, it's like, okay, what is my initial parameter estimates? What's my range, right? From our graphical exploration before, we know that a range of, -2 to 2 covers a lot of different shapes, right? Now I have an idea of where this should be, right? Where, from what you saw in my weight plot, right? And from what these, again, these covariate, this DLCD weight value means, right? I would expect in my case that my DCLD weight would be, maybe 1 in between 1 and 2, right? Just based on my plot. So I hope that makes sense. I'm sorry if I'm harping on it and it's a little introductory for the class, but again, this way of thinking through your models and really understanding the math, I think is critical to becoming a good modeler. Instead of just pushing buttons. And so I might use 1 as an initial estimate here. Why would I specify -2 there, right? If I see a relationship like this in my data, why would I start with an initial estimate that, goes the opposite direction? And, that can cause headaches, right? Because if you start your initial estimates in the wrong area, your algorithm can hit a local minima. And yeah, so again, understand these models. So we're done there, right? This model will run now. The other way you could have done this is launch that in the model editor, edit meta model. And there it just gives you a bit more, it'll give you pop-ups if you're making mistakes in your code, for example. I might be able to show you that quick. Doing on time, we're okay on time. But here's my error model, right? If I were to forget a parenthesis here, right? It says whoa line. So this is kind of useful. I think if the more you work with the syntax, the better you understand it, the less useful this will become. But if you're just beginning, then the model editor can be helpful. And of course here, you're able to see your data set, all this stuff. I'll just exit out of here. So, okay, so now we're going to run this model, fit meta model. Just going to fit it. So now this is going to estimate my fixed effects term for that DCLD weight. And we'll go back and we'll take a look at the covariate diagnostic plots. Should be pretty quick, right? You see where it's kind of hovering in around 1.87. Should finish up pretty quick. Okay, we're done. We can refresh this. Weight on clearance, right? My initial estimate was 0.87. If we just look for ha-has at the omega terms, so between subject variability terms, we can actually, these are variances. So if you take the square root of them, they approximate like a CV for a log normal distribution, which is what the error models we're using, essentially it approximates. So for our weight on clearance model, our between subject variability and clearance is 20%. Now, what was it in the base model, right? I don't recall. Well, you can check it quickly. 37%. So by adding weight to the model, right, we've reduced our leftover between subject variability by 17%. So that's the type of thing that you want to see, right? If your covariate, if it makes sense to put it into the model, right? The objective function. So here, the reference model, right, is 2, which is our base model. That's correct. By default, when you use the model duplicate, the model that you duplicate from is going to be treated as your reference model. You can always go into Piranha and change it. There's this notes and info. Again, I know I'm touching on just like random things in Piranha. Just explore it. It's pretty intuitive. Here you could change that reference model. And why might that? You can add notes to the model, right? Why might that be important? Well, you want to make sure that this calculation here, the change in objective function, right, is using the right reference model. And here we can see that weight, adding weight to the model reduced the objective function by 113 points, and that's large. So we know weight is an important covariate in this model before we even look at the diagnostics. But now we'll go ahead and look at the diagnostics. And now, would we want to look at parameters versus covariates? Well, we could, but recall that we'll definitely still see a relationship there because it's the individual parameter estimate. What we want to look at are the ETAs. And I think we can compare, again, I'll show it for the other model too when it comes up, just for comparison. Eventually it'll be here. So remember, volume, weight, we did not add a covariate there, right? But for clearance, now these are ETAs, right? So what is again, what is the ETA, right? It's the size and the direction of the error term based on the individual's data. So here it's saying, look, the ETAs are negative for low body weight patients, but they're positive for high body weight patients. Very often these plots, you'll have like a line here. That would be the reference line. Now let's look at clearance. You see what happened? So now our ETA term, right, in our model is basically evenly distributed. It's gone, right? So that is, again, suggesting, look, when you add weight to your model, now the miss, right, for a patient across the body weight range is essentially the same, right? So adding weight into the model now allows your TVV to be more accurately predicted based on body weight. I hope that makes sense, right? If we continue to flip through here, right, volume, creatinine clearance, there still looks to be something there, right? Adding weight to the model seemed to have fixed the creatinine clearance relationship a bit. So again, that's because creatinine clearance and weight is correlated. If you still saw a pattern in here, you might think, you know, maybe I need creatinine clearance too. So I hope this is helpful, right? Age still looks about the same, right? Gender, there still looks to be a gender effect for volume, not so much for clearance, right? So what would my next step be here? Probably I'd go and run a single covariate model for volume, right? Look at those diagnostic plots. One other diagnostic that, again, I don't see that much, but when I took my original nonlinear effects modeling courses with Stu Beal and Lou Shiner, one of the things that they proposed was, instead of looking at your ETAs, what you want to do is you want to calculate a parameter which would essentially be your CL, right, minus your TV CL. I'm not going to actually do it, but you might call this, D delta CL equals, right? And we would then use the delta CL in those same types of diagnostic plots. And think about what that is. The reason that they proposed this type of transform was that it's essentially the same type of plot as looking at ETAs, right? But you're looking at the ETA in units of your parameter estimate, in like the space of your parameter estimate, right? So here the CL minus TVCL is analogous to your error term, but it's in units of clearance. And the reason, again, I use this for many years, was that depending on the type of error model relationship that you specify, you might sometimes see patterns due to the fact that you've exponentiated this, right? And not necessarily that you could see a relationship that might not be real. So again, just maybe a little of a sidebar, but I've always used that parameterization myself. And you can add that, you can add that to code. So I'm going to close that without saving it. So yeah, I think what we wanted to do next is go back to our slides. And okay, so I think as you're beginning to learn modeling, just doing a quick time check here. As you're beginning to learn modeling, I would encourage you to do your stepwise covariate model building. I would encourage you the first few times you do it manually. Add your covariates one at a time, look at the diagnostics, take your time to understand what your data is saying to you. It's very helpful to do that manually for the first time, if you have the time. For RsNLME, to save time, and stuff like this is available for other engines as well. We have a couple of automated covariate search algorithms. I'm going to take a look at the stepwise covariate search, and what this does is it basically automates runs of your candidate covariate models using a predefined selection criteria. So you launch this through the model executor UI by selecting covariate search stepwise. You have some setup criteria right here. The criterion for model comparison and keeping covariates in the model is -2LL. And to add a covariate, the significance of the model needs to be, the p-value needs to be greater than 0.01. And then once you have your full model, to get rid of a covariate, the p-value has a tighter threshold. It has to be more than 0.001 to get rid of that covariate. But you can adjust these. This is kind of a typical way of doing this. So we're going to basically step through the way by which you'd set up for this and execute it. And essentially what you do is you take your model and you add all your covariates to your model that you want to test, and you specify the relationships to be tested. Now, for example, the model below will evaluate weight, age, creatinine clearance, and gender on CL and B1. And you see here, what we've done is just like I did for the single covariate and weight, right? I added covariate for age, for gender, for creatinine clearance on volume. And I also modified the clearance, weight, age, gender, creatinine clearance. I've created my fixed effects for all of these. For covariate search models, you need to include this enable flag. And this is essentially it goes from 1 to n being the number of covariate effects you have, or 0 to n, sorry. So 1, 2, 3, 4, 5, 6, 7, 8, right? And we have 1, 2, 3, 4, 5, 6, 7, 8 that we're going to be evaluating. And this is just how NLME uses the enable to manage the creation of the scripts to run the automatic covariate runs, and also the display of the results. We can take a look at that, right? So I think what we can do is go back to Piranha. And I have an example that we'll switch over to, because the automated covariate search, you need to do a bunch of runs and it takes a long time. But the way we would do this is essentially go to our model editor. This is how I do it. So we'd run this. Now we're creating a new model, and we're going to use this for covariate search. And do this pretty quickly. Right, so we have a PK model. We know it's a 2-compartment model. We decided on our multiplicative residual error model. Right, next. We have our exponential eta terms here. We're going to come back and take a look at this style after I've added a few covariates, because you see there's different options under here: product sum, right? We're going to take a look at what that actually is, because it gets back to your covariate model structure and understanding what selecting one of these means graphically, okay? That's why I brought that up earlier on. So if we go to our covariates, we're going to add weight, age, gender, and creatinine clearance. So weight is a continuous covariate. I'm going to center it on a value of 70, right? And the effects, I'm going to put it on volume and clearance. You see it pop up over here, right? Again, if I didn't know when I was doing this manually how that syntax worked, I could have come here and just then, okay, now I see my example, copy it, and then just exit out of this. And I have my answer, but we're going to continue to go through and build this full covariate model. So age, continuous, value, maybe the again, be selecting the median age in your data set. I could go back and look at that correlation plot, to look at the distribution, but 45 is what we use here. Whoops. So I forgot to add age to my volume and clearance. Right. My next one is creatinine clearance. CRCL. Mean value, the median value is around 90. Again, pick something that makes sense there for whatever you need to do with the model, VNCL. And then finally, we have our gender, right? This is not continuous, it's categorical. And for categorical covariates, you need to specify the levels. If it's character in your data set, you should specify like labels here, but here we're numeric, so you don't have to do that. Only applicable if covariate is of class character. And then volume and clearance. That's one of those things where NLME is more flexible. You can have character variables in your data set, and NLME can handle them no problem, which is different than other nonlinear mixed effects modeling packages. So it's a blessing, and but you just need to pay a bit more attention if you're using some of that functionality. Okay, so we've added our covariates, right? They're all in there. This model should look like what I showed on the screen before. They've been added here. Now we go to our fixed effects, and again, your initial estimates. You should have some idea from NCA, at least something close. For my example, I'll just type in what we had from our base model, 7. And again, for your initial estimates for these weight effects, I know we knew weight was around 0.8, right? If you ran all your single covariate model runs, you'd have an idea, you know, where these lay. I think DVD sex, we saw a reduction, right? So we might want to start negative 0.1 for the sex covariates, negative 0.1. I guess we can leave the other ones as 0, which is by default for that type of model, no relationship, and it'll get pulled in the direction that it needs to get pulled in. Random effects. So we have volume and clearance. Now notice here, I forgot to take my random error terms after V2 and CL. Let's see, hopefully I can go back and structural parameters, right? We want to uncheck this, then that disappears. Okay. And I didn't finish this. CL 0.1. Just a reasonable initial estimate. Okay, so this looks pretty good. Next, we won't use any additional, or I'll touch on that when we get to the simulation. Then we need to map our variables, ID time, DV, weight is weight, age is age. This is similar to what we did when we created our base model. Granting clearance and amount. So now we can save and exit this model. Go back to Piranha, refresh. All right. And you might want to, you know, give this a name, covariate search. Okay. So at this point, just refresh. At this point, what one would do, and I'm not going to actually do it, but I'll show you how you would do it, is you'd go to execute meta model. Instead of running that directly, right? And under the run mode, you would select the covariate search stepwise. And then here you can edit these if you know you like. For this particular example, this would be appropriate, you know, selection criteria for adding and removing covariates to the model. And then you just hit run. So you set the model up and you run, and NLME will go through and execute a stepwise covariate search. Again, if I launch that now, it'll be the last exercise we do for the class. So what I'm going to do now is come back over to my covariates directory. So again, you can do this in Piranha, right? I have this Project Dontabhaktuni area, and I also have like subfolders within here. So I can go to my covariates, and this is where I reproduce the work that we've done so far. However, I have the covariate search model in here, right? I ran it last night. This is exactly what we just created. And the output from this, essentially there's two, it'll be placed in a folder, right? Stepwise. I ran it twice, so we have two folders. If we go into this folder, we see the output from this. And the output is not, it's kind of abbreviated compared to what you get for a single model run. If we look over at files, you see a lot of output here, right? And if you go into these text files, it's like output from the individual runs. But the important pieces of output in this set of files is the overall, and then down here we have stepwise text, right? And I have a slide on interpreting the stepwise text, right? So I'll go and open that file in a minute, but essentially it looks like this, where it starts with a base model, and it says, okay, my base model objective function is minus 2032, and I'm going to find the effect that reduces that log likelihood the most out of the set of covariates that you've selected. And then it lists the first run. Here it's volume on weight. And it says, okay, the objective function from that run was minus 2,117.68, right? And in order for me to keep that, that needs to represent a greater than 6.63 unit drop in the objective function. Now, where does the 6.63 come from? That comes from the chi-square distribution table that is associated with a 0.01 p-value for a change in the objective function. So the minus 2 log likelihood is a statistics that you can compare using chi-square distribution characteristics, right? Again, I'm not a statistician, but this is what's going on. So it looks at the objective function, it adds 6 to it, and if it's less than the base objective function, it says, aha, okay, this one's important, right? The next one, you see this X here? So it did the same thing for age on V. Remember, our diagnostic plot suggested that age might not be so important. Well, here's evidence that it's not. Adding age to the model reduced the objective function. No, it actually increased it, right? So minus 2032 is less than 2028, right? So it actually went up. So this model, it says, nah, age is not important. So it'll reject that one. So it keeps doing this. And then what it'll do is it'll pick the most influential one. It says, okay, say we'll go look at it, but say it's volume. I'm going to keep that and then add everything one at a time. And then it'll get to the point where it's added everything it can. It has a full model and it will reduce it one at a time. And in the end, it'll output, you know, what your final model was. In this case, it was the 9th model that was run, and the covariates were weight on volume and weight on clearance. So what that's saying is that, you know, creatinine clearance, all these other things dropped out and they weren't important. Now, a good modeler would go back and take this model, run it, look at diagnostics, you know, make sure that they're comfortable with the relationships they see. And you know, again, the automated, yes, it'll do the job, right? But you know more than the computer does. So always go back and kind of check the results. Just, you know, for explanation's sake, right? You see this 1,000, 0, or I don't know, what is that, a million, 0, 1, 0, 0, 0, 0, right? Where that's coming from is that enable character. So each one of the enable characters, there's 8 of these, right? The NLME will put a flag there, right? So if you recall from our code, right, volume on weight, right, DVD weight was our first enable 0 DVD weight. So that's the first position, right? So it puts a 1 there to indicate, okay, this is my volume on weight model, right? The second one would be age on weight. And as you look down the row, it'll have 1s in the position of where the covariates are fitting in. It also gives you the text, but that, you know, that's what that number is. It's all that it is. Kind of useful. So, and I mentioned the overall. This is the overall summary. So let's go back and just take a peek at those. But I basically explained what they are. Stepwise text. You can just open that quick. So here's my first effect, right? It's going through. Age is not important, right? Gender came in, that was important as a single covariate, right? So it runs all these and it says, okay, I'm going to keep weight, right? And now I'm going to retest these other ones. So adding creatinine clearance to weight actually, you know, was important when there's only these 2. Adding volume to weight, adding age on volume to weight on clearance. Hopefully this is clear what it's doing. So it gives you this big output. And at the end, it basically says, okay, this is the model that I've chosen. So pretty useful, actually. Overall, we'll just take a quick look at this. I'll be honest with you, usually I just jump to this, right? I'd open the overall and I would go through and create a column in Excel just to look at the change in objective function for my various models to check, you know, what was going on. But you know, a couple of different ways to look at this. So now, you know, what we have is the I think I'll just work from here now, if that's okay with everybody. So now I've done my covariate search, and it said, okay, my final model is a model with weight on clearance and volume. So what I would do at that point is I would go ahead and create that model with weight on volume and clearance. This is my, I'll call it my final model for the purposes of this course, right? But I would do more, diagnostics on this probably at this point. But we can run that. I've run it in this example. We can go and take a look at, our parameter estimates, our, again, from our base model, between subject variability 36, my final model has come down to 23, all good things. These estimates for my fixed effects look good. They're estimated precisely. And we can go and, look at some of these scripts. Again, let's take a look at Ada's versus covariates. If I can double click fast enough. And what we'll see now, right? Volume versus weight. We'll flip through them quick. Clearance versus weight. Grant and clearance, age, right? This is all looking pretty good. Gender. So that's a good set of covariate diagnostics at this point. So I hope that gave you like a good visual sense for the types of things that, you want to look at and see. There are again, a number of other diagnostic plots that are used to look at the data for certain features. But I mean, that is the core of, again, running models, iteratively evaluating what the model is actually doing, how it's changing the fit to the data, looking for drop and objective function. It's like a multifactorial evaluation that the analyst is responsible for as you do these types of analysis. Yeah. So combined goodness of fit, maybe we can just do that for the right, compare our base model to our final model quickly. Right, so here we have our base model. Right, here we have our final model. You see a great degree of improvement in the pred. Right, so again, the base model has no covariates or anything in it. So it's just predicting the same concentration for everyone in the data set. After you add your covariates, right, now it's able to, independently of the residual error term, do a much better job, fitting the data. And the residuals have been improved as well, right? So that's kind of, again, one of the nice things in Piranha is the ability to, select multiple runs and do quick comparisons. We'll close that out. Close this. Now, what's next? We still have still good on time. So what we're going to do next is we're going to use NLME to do a visual predictive check. And it's a visual predictive check. Forgive me again if this is too basic. It's really a key model diagnostic. It's simulation based. It's one of many simulation based diagnostic tools, but it's really a key one. And what it does is it allows holistic view, again, not in statistician terms, right? But the way I look at these is it really allows you a holistic view of how your model is performing, across all of its components. The diagnostics we were looking at earlier, you're looking at your residual error term, right? You're looking at your covariate models, right? Simulation diagnostics really allow you to answer the question, how is my model, right? Is it able to simulate my analysis data set, right? All the features of it, right? And if not, where might I need to tweak it? And in that, hopefully the answer you're looking for is, well, yes, I'm confident it's simulating my observed data set exactly, all of its features. Why is that important? Well, then I have more confidence that I can use my model to explore scenarios that, might be a bit different than what my analysis data set was. And how different, that again, comes down to a lot of factors, right? You don't want to develop a model in one pediatrics in one disease area and then use that same model to try to simulate adults in another disease area, right? So again, probably some of this stuff is pretty straightforward, but just trying to make the point. So essentially what you do is you take your model and you simulate a large number of replicates, and then calculate your percentiles with confidence intervals around them, and then you superimpose this over your raw data. And for your raw data, you also do the same thing. You calculate your associated percentiles and confidence intervals, and they should overlay. And if they don't overlay, then it's suggesting that your model might not be predicting certain elements of your data. It's quite simple to do in RsNLME. You essentially launch it via the model executor, and the run mode you select is visual predictive check. You select your number of replicates, and you go. And this is the type of output that you can get. And we'll actually go ahead and at least look at the R code that I used to generate this. And here, so what you see in the colors are from the simulation. So you simulate, 100, 1,000 patients. You have to be careful because these data sets get huge very quickly. But you simulate a large number of subjects, and then you do statistics on that simulation to get, a line for your 5th percentile, for your median, and for your 95th percentile, and then you calculate confidence intervals around that. And then you superimpose that on a plot of your observed data with, in this case, lines for my 5th, 50th, and 95th, right? So here you can see for the median, this model actually is doing extremely well, right? The observed and the predicted median are, overlaid exactly. Of course, this is a simulated data set, right? Best case example. But that is how you would interpret this kind of thing, right? If you look at the 5th percentile, right? Your observed 5th percentile is somewhere around here, right? Whereas my model kind of deviates from that a bit, right? So that might be a signal that, okay, for some reason my model's under predicting in these in the distribution phase, right? And that might be something that you'd want to look at. If you had a drug where you wanted to do simulations and you knew the PD effect was driven by concentration in this area, you might say, all right, if I'm going to run simulations, I got to get this better, right? I want that right on top of my observed data. Of course, your observed data is always just a sample out of a population, right? So it's, again, it comes down to really just making a decision. Is it good enough, right? But the VPC is a very, very effective tool, right? Here, it's slightly over predicting, but you see the 95th percentile for your observed data is on the edge, close to within the range of the confidence interval around the predictions. That gives you a sense for how to interpret these things. So now to do this in Piranha, what we would do is we'd essentially, I think I have a folder that I created for this VPC. So essentially what we do is we'd fit our final model, right? And essentially you fit it to make sure that you have the, the right parameter estimates, because this is what's going to be used as your terms when you run the simulations. No other changes are required to the model. Unlike when you're doing a stepwise covariate search, you have to set it up for it. You can just feed this into a VPC run. And the way you would do that is essentially, again, right click on it, go to execute meta model. Wait for this to launch. And here, instead of the simple run mode, we would select visual predictive check. We would select our number of replicates, right? You need to be careful here though, because the tables get huge, right? And I'll show you why, right? And we have this add table button, right? So this add table button is basically how you specify, okay, what kind of output do I want well, actually, I'm getting ahead of myself. I'm sorry. I'll remove that. That's for simulations. We are ready to run a VPC right now. And again, the number of replicates, we have 100 subject data set. So 100 replicates of that would be 100 times 100. When you run these types of diagnostics for the final kind of cut that you're going to include in reports and make your final decisions on, you want to use a large number because you need the number of simulations. The higher number, the better you get in terms of those confidence interval calculations. But these data sets can get huge. I won't run it. Rather, I'll show you what the although that it's pretty quick when you run that. I probably could run that, but I've already run it here, and the important output will be in the again the folder. When you run a VPC, it creates a VPC folder. If you don't see these folders in your R, I'm not sure if in your Piranha, I'm not sure if I covered this or not. You're able to select what you see in terms of folders through this menu up here. If you select no run folders, it hides them. You can show NLME folders, right, which would just be the folders that have the outputs from various runs. Or you can show all, and that would show like the Piranha. Piranha will keep a backup of all the work that you're doing if you have it configured in settings. But yeah, that's if you don't see those folders, that's why. So I just leave it on NLME folder. But if we go in here, the results of the VPC are right here. And the main results that we're interested in really are in this pred check. So this would be your observed variables. This is like it's like a copy of your original data set. And then the pred out CSV. And the pred out is essentially your simulation output. So here, if I just quickly go down to the very bottom, right, you see there's 110,000 rows in this. And I think I selected, I'm not sure how many replicates I selected for this when I ran it, but they get large quick. All right. So, okay, what do you do with this, right? Well, the output from a VPC, right, there again is a package in R called Tidy VPC that was developed as a collaboration between our software development group and our consultants. And we are integrating this with Piranha in the next release. But for today's course and the way you need to do this today, you would import this pred checkout and the simulation output into R and use the Tidy VPC package manually to generate the VPC plot. So how do you do that? Well, I have a script here that I prepared. Again, I will share this with the class. So I've run my VPC. I have these data sets that I just showed you. So I'm going to load the Tidy VPC library, set my working directory to where those files are, and then I'm going to read my, well, here, let's just do it, right? I'm going to read a data set that I'm going to call DT-OBS data, right? Read CSV, pred check. We've seen read CSV before, right? So now I have my observed data set, right? It's brought into R. Here it is. I'm going to do the same thing for my simulated data set. And then I am going to create a binless VPC plot using syntax that's associated with a Tidy VPC package. Again, to understand that package, we have in the reference material that I provided to the class, we have our vignettes. If you look at Certara R packages, Tidy VPC is in there. So there are tutorials for how to install it, how to use it. And this is where you go if you have questions. We're really working very hard to build out our documentation such that it's immediately accessible and presents real-time examples for how to do these types of plots. Okay, but this is where this code is coming from. And to create a binless VPC plot, so the binless in a VPC, the concept of binning is very important, because think of a bin as a grouping of your data in your data set. And if you consider complex population analyses that data sets may have multiple studies with multiple different dosing regimens, multiple different doses, right? The way you group those data to basically calculate how my model is performing, right, is defined by bins. And there's many different methods to to bin data on. Again, it's really beyond the scope of today's discussion, but if there's plenty of good papers out there. One of the methods that we implemented into tidy VPC was a binless method. So the binless method uses additive quantile regression to figure out essentially, where the summary should be made. Again, not a statistician. That was Chris Jamson, used to be a consultant at Certara. He drove that paper. So there's a paper on that, but you can execute this within the tidy VC package very easily. Essentially what you do is it's a call to the binless VPC, where you identify your observed data, you identify your simulated data, you call the binless method, and then run this VPC stats, and then you can plot this object. And I'll just go ahead and run this. This takes a second because it is doing some regression in the background, as opposed to definitively just setting bins based on some kind of method. But you'll see this this plot will produce the VPC eventually. There we go. Right, it's a nice VPC. Again, that's the picture that we saw on the slide. A bin VPC using a method called Jenks. So again, there's methods that determine how the bins are created. This will create a different plot. Now this is more informative in terms of these black lines basically show you where the bins have been created using the Jenks method. There's other methods where you can set these manually. You can use nominal time. So there's a lot of options, and one might be thinking, okay, what might those options be? Just another quick thing to show, there's a package called Egg that allows you to arrange ggplots. So another interesting package to understand how to use if you're if you're learning R, right? So that's what Egg allows you to do, right? Base R allows you to kind of split up your screen. ggplot doesn't really allow you to do that, but the package Egg somebody wrote because they wanted to do that, and now you can. That's where the Egg comes from. Now, the nice thing about tidy VPC is if you don't want to deal with all this code stuff, right? Again, that underlying theme for why we built these tools the way we have, there is a RShiny app, right? So you can basically run this RShiny app. And this is what I would recommend for beginning analysts. This will pop right up. And essentially what this is the GUI for tidy VPC. And the way it works is that you upload your data set. So here, I'm going to browse to my, let's see, so I'm not even close to where I need to be. Hold on just a second. Well, I'll just browse to it. I don't know where it is. So I will go to my data, Piranha. If you launch it from within a working directory where you have the path set correctly, it'll go right where you need it to. But I'm going to go to my Project D folder, Project D, and my VPC is working with this one. Right, and I have my observed data here, PredCheck CSV, right? And then I'm going to browse Good, it stayed in the same place. I print out. This works for, basically, this is not NLME specific, I should add, right? If you have software that generates visual predictive check output, you can use it with a tidy VPC package. So I've uploaded my data sets, and I'm going to select my variables. X is DV, Y is DV, X is my independent variable. And then I can come down here and, you know, if I want to bin on the X variable, plot. Right, so there's a you know, plot binning on the X variable. If I wanted to look at a different binning method, Jenks, and again, what these are, you can look them up. They're just different mathematical ways of binning or setting these intervals for the VPC. For this data set, it's not so important, but if you had a data set, like I said, where there's multiple studies that you're trying to come up with a reasonable plot for, that's when it comes in. So I won't spend, you know, any more time on this. Really, we've implemented the binless methodology into this tool as well. Just pick Jenks, let that run. Still have about 10 minutes, which will be perfect because I just want to show how to run a simulation after this. You know, I apologize for the delay here. It's because of the Zoom meeting. Okay, so there's Jenks. You see these bins are different. This one's wider here. And again, the nice thing about Tidy VPC, the app, is that you click on this button here. And what it does is it provides the code that you can then copy into R. And you see a bunch of stuff in here that you might be, you know, what the heck is that, right? This is the value of these GUI apps, because now you know that there is a scale fill manual command that you can run within a ggplot, and that's how you talk to it, right? And you can bring this into R and tweak it and see what it does. So it's really a powerful tool to help you learn pretty sophisticated R code. Yeah, so I can just dismiss this. I won't bother bringing that into R. There are other things we're working on. This is going to be available in the December release. It is available now as a pre-release copy. If you're interested in getting, you know, your hands on this tool, please let us know. But this essentially is a version of Tidy VPC. It's the next version where we've implemented reporting capability into the tool. So if I just come down here and you know, plot this. This is you know, again, the Tidy VPC app, but we've included a lot of functionality in order to be able to interactively you know, modify this plot. And again, the changes that you make are returned in code if you wish to get that code. But the new functionality from this is the ability to tag diagnostics as you work through your analysis. So if I tag this VPC plot, so tag it, yeah, tag that one, and then maybe I'll generate another one here. Let's see, inputs, quantiles, controls. Well, I guess I'll just tag one. That's enough. If I go to my tag documents, right? Here's the document that I tagged. The code that I used to generate it is here, right? And what I can do is download the script that was used to create that code, or I can go to my report tag And for all my tag documents, so I could be assembling these as I go through my analysis. I could have a group of them, and I can drag that into a report document and then essentially generate a report from that, right? In HTML, Word, or Doc. And if I hit download report, all right, I have another example I can show you on a different machine here. But this will generate a Word document through R Markdown, and will also give you the R Markdown code where you can essentially make a reproducible copy of your full analysis. So, I mean, that's where we're going in the future with that. Maybe a bit of a sidebar, but that I think is going to be an extremely useful addition to Piranha in terms of expanding the extent of workflow that's supported. Okay, 10 minutes before I'm going to give some time to Aruna. So the last thing that I wanted to show today was simulation. So essentially, we have our final model. Now we want to do something useful with it. So what I'm going to do is show how to create a simulation using a new dosing algorithm from our final model. So we have this 24-hour times 2 dose. We're going to look at a Q24-hour times 7 doses. So we're going to create a simulation data set with multiple dosing columns. We're going to execute the simulation. We're going to plot the results. Now, there's many ways to create simulation data sets. We learned some in earlier lectures where you can specify distributions for the covariates that you want to end up in your data set. And I encourage you to go back and learn how to use that code. For today's demonstration, we're going to take a simpler approach. So we have a data set with demography in our patient population, right? So we already have a set of demography that we can use from our data set. We have 100 subjects, which is a decent amount, right? And what we're going to do is we're going to modify that data set by only keeping the first dose record for each of our 100 subjects. So we'll have one row for subjects. And then what we're going to do is we're going to add 2 dose columns to basically tell the data set, all right, we're going to, instead of looking at 100 milligrams Q24 times 2, we're going to give 100 milligrams every 24 hours times 7 doses. And the way we do that is with this ADDL, or additional dose record, and interdose interval variables. And I'll explain how that works. So if we go back to R, I have my sim script here. And essentially, we're going to set our working directory. We're going to read our original PK data set in, because that's what we're going to be modifying. I've just called it my data in this. What do I still have something open here? Bear with me for 1 second here. Stop. Okay. All right, try this again. All right, so we have my data, right? That's our original data set. Now what we're going to do is we're just going to pick out the first row for every subject, right? And the way we do that is we have my data and we assign it, right, to what is going to be the output from this next string of commands. If you want to do that. And we're going to take my data and we're going to pipe it to the filter command, where we're going to keep the row of time equals 0. So we're then going to have a 100 row data set where time is equal to 0. And then we're going to pipe that, and we're going to mutate that data set to add a column named additional, where the value is 6, and a column called interdose interval, where the value is 24. And if I run that quickly, I can go to my data, and this is what you'll see. So 1, 2, 3, 4, 5 down to 100, and I've added the ADDL and the interdose interval. Okay, and all you need for simulations in NLME is the dosing. In the simulation run, we're able to specify tables that we want for the output. And I'll show you how we do that. But we have this dose record, right? And what this dose record says is, okay, at time 0, I'm going to give 100 milligrams. And after that, I am going to give an additional 6 doses using 24 hours as the interdose interval. So another way to do this would be to, for subject 1, list 7 rows and have time equal to 0, 24, 48, 72, right? In other words, 1 row per dose event. This is shorthand to allow you to specify like multiple doses in a single row, right? So I guess looking, I got 10 minutes, I'll be quick here. So we write this file back to our directory, because we're going to pick it up to run it with a simulation. And then what you would do is go over to Piranha. I'll just show you how to do this quickly. Go back, I have my simulation folder, right? I have my simulation run. Again, this is the, this is the same model, your parameter estimates, make sure they're the final ones that you want to use. But you would simply right click on this, execute meta model. There's really one part that I need to show you in here that's important for running these simulations. It launches. So we have the run mode simulation. Okay. It allows you to select the number of replicates. And this is where you need to be careful, right? Because what we're going to do for the simulation, remember, we only have 1 dose record for each subject, right? So if we simulate without adding a table, it's just going to give us a table where there's a 0 at time 0, right? So what we want to do is say, okay, I want you to create a simulation table, and the times I want you to output, you can list times. So you could do 0, 0.5, what have you. Or more often, it's convenient to use a sequence command. Now, the sequence command, you'll see this in various languages. You can do this in R, right? So what we're going to do is create a sequence of values, right? From time 0 to time 192. So sequence from 0 to 192. And how would you know how to do this syntax? You'd go to R and you type $sequence, right? And it would give you the syntax for achieving this. And the next value is essentially the interval. So I could do 0.1. Now that would be a huge number of rows, right? I could do 0.5, right? That would cut it down some. But what you need to be careful is, okay, if I used a 1, that's 192 points, right, per subject. And I have 100 subjects in my data set. So that's 19,200 now. And if I picked like 100 here, then you're talking about a spreadsheet, a CSV file that's going to have like 1,920,000 rows, or so they get big quite quickly. So based on what you're trying to do, maybe for a final kind of simulation exercise, that would be appropriate, but they can take time to run. So I mean, I'm not going to run this, but I think I cut this down to like 5 replicates, so that's 500 subjects. Still a decent number to do what you want to do. And then here, is where you would list the variables that you want. So I would type in C, right? C obs. This is case sensitive and dependent on what you have in your data set. If I wanted to stratify by variables, I might put some stratification variables in here. This button will add structural parameter estimates, right? If you wanted to start with those, so C, C obs, I think you get the point. And then essentially you'd run the simulation. And what you get, I close out of this. I know, Aruna, I'm 1 minute over, I'm sorry. What you get would be this sim table 2 CSV, right? I'm not going to open it, rather I'm going to go back into R and import that into my R session. Right, so I've imported it. It's there. Can just run that quick, right? So we see it's got all our variables: ID, time, C, obs, weight. You can see the parameters that come in. So you can do further plotting with. And I just used ggplot here to do a quick summary. I faceted by gender, for example. VPC plots, it's always useful to, if you have different subgroups within your data set, occasion, right, that Sergey talked about at the very beginning, right? You could facet your plot by occasion. And what you'd want to see there is that your VPC is, again, you're simulating simulating the characteristics of your data set. So again, this data set is kind of large. It's finished, but it just hasn't displayed the plot yet. I think at this point, it will come up, right? But I won't wait. I'll go to my PowerPoint. And we talked about this, right? This is the, right? This is the, the interface. And this is a plot that I would generate from R, essentially a multiple dose simulation. And from this, if you were looking to define a multiple dose regimen that exceeded a C trough threshold, right? You could take this data and say, okay, what percentage of my patients that simulated met that criteria? Based on this dose regimen, maybe try some different dose regimens. That's the type of thing that you might want to be able to do. So that's it. I hope today's lecture gave you a really good feel for really the kind of the core steps in a pharmacometrics analysis workflow. And yeah, again, thank you for the opportunity to to let me share this stuff with you. I do appreciate it. Back over to you, Aruna.
Thank you so much, Keith, and sorry for the last minute rush there.
No,
again,
a lot of material to cover. Yeah.
I encourage all the participants to please keep going back to the material that we are sharing on the YouTube channel. I know this may be quite a bit of information to get in, a 2 hours span. So that is also one of the reasons why we record everything, so you can keep going back to it. And sometimes if you have forgotten some aspects, you can always go back and refresh it. Again, wanted to give you an overview that we had over 100 people who applied for this program, because we had to keep our numbers limited. We actually we invited about 94 participants to join this program. Again, this is the distribution of the group that went through this program along with you. As you can see, most of them were PhD or postgraduate students, and we look forward to seeing you back in our future workshops again. For those of you who don't know me, I am Project Dontabhaktuni, and to bring you to what the objective of Project Dontabhaktuni is. So we are a nonprofit organization created to support scientists and students and postgraduate students around the world. Our theme is to support you by growing your careers, by providing you workshops and training programs and mentoring opportunities. How can you support us? You can support us by joining hands with us, taking advantage of these workshops, and of course, by stepping up to become mentors yourself. I know many of you actually accepted our request, and I would like to acknowledge all those who actually took on being mentors. Again, thank you so much for taking on being group leaders and mentors for the various participants who were part of your group. I do know that in some cases, you really had to go above and beyond to reach your team and interact with them. I would encourage you to continue to do the work. Also wanted to share that we said that this is going to be a 3-month certification program. What I also got hearing from many participants was that they needed a little extra time. So we would actually give you an additional month for you to go over all the homework assignments, and would strongly encourage you, if you would like to get a certificate, we would like for you to submit all the homework assignments. If you're having issues or not able to complete the assignments, please reach out to us. Either one of our team members are going to support you. If not, we can get you in touch with the trainers who can support you as well. However, we would not know if you don't reach out to us. So please continue to reach out to us. Let us know how we can support you. Again, want to acknowledge our Module 3 instructors, Keith, Anna, Mauli, who have been extremely instrumental in making sure that your RsNLME installation would happen, that you actually get to understand the concepts, and thank you for all your feedback. And of course, a workshop of this magnitude would not have been possible without the unwavering support of our board members and also our volunteers who have played a very critical role. I would shout out to Krishna, who has been instrumental in sending all the emails, keeping you in touch with all the assignments that are coming up, and Arun, who has been a great help in organizing all these Zoom workshops. Sabiha, who actually helped post many of the videos, Ramya, who has been instrumental in managing many of the meetings as well. Thank you all again for all your support, your participation, and for being here and for giving us this opportunity to share this knowledge with you. As I said, you will have a month